Now this should be T. Excuse me, sir. That is T. I think that we have that. This place with this place is F. And they have that this place with that place X. So this is the thing, and if you take an elemental volume like this, for the field of this nature, of course you know that sometimes when you analyze something, when you want to analyze an engineering system, you take the differential volume. So the differential volume goes and of course what goes into an extended surface, a thing like this is what? What goes into it from the surface like this is what? And what comes out is, so heat goes in. So you can denote that heat to be, call it U, US. And what comes out is what? U, X, plus U, X. So that's what comes out. It goes in and comes out as US from US. Of course, this has a lateral surface, and heat also goes out from the lateral surface. So the heat that goes out from the lateral surface is, we can say is US goes out from the lateral surface. This elemental volume, of course, this differential volume is part of X, but we call it, it's part of X, but call it dx. 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 So I think that you can understand what I'm trying to do, what I'm talking about. So this is the base temperature. Of course, you know the ambient. Ambient is the TA. So, and temperature, the base temperature. Okay. What next? Remaining US from UX comes out. So finally, we can say that base temperature of phase is equal to surface temperature of bulk material, which is equal to T0, then ambient temperature. Ambient temperature is what? TA. Then fin length is what? L. That is this. and fin thickness. Fin thickness is what? And fin width is what? B. So okay, so fin surface heat transfer. Is H. That is on the top. Bottom and the side surfaces. Fin material. Fin material density. Of course, the material has weight, is equals to rho. Fin material thermal conductivity, of course, the ability to transfer heat. Any material that has that ability to transfer heat has a conductivity, and that conductivity is the constant. Fin material thermal. Equal to K in watt per meter per degree centigrade. So if we have specified that, of course we call this figure 2.41. We call it fin, rectangular fin. If we have specified that, we now say we apply the energy conservation. Energy conservation. The control voltage. The control voltage shown in figure 2.41. The energy can flow into and out of the control voltage. And see, so we apply the energy conservation equation to the control volume. That's used the control volume, which are called the differential volume. So the significant energy then flowing into and out of the control volume is heat energy conducted through the control volume. The significant energy within the material is what? The significant energy within the material is what? That's sensible internal energy. The sensible internal energy U, where the U is equal to CV T. Because the material is incompressible. Because the material is incompressible. Density rho and the specific heat in this situation there is no work. There is no work done. So, okay. And we can know the relation. From this source. First law or energy. So the first law of energy conservation then is that E dt U dt Euro AB the X is equal to Q X minus Q X plus the Q X minus Q S minus QS, which is equal to minus Q X plus, I think this should be decimal decimal square of think equation that. Okay. We now have that we now have that rho A, B, du, dt is equal to, of course, evaluating is very this is equal to dq x all over dx, dx all over dx, minus so we give us that when attention, if you have the x here, and we have that the u is equal to cv with the decimal cv, and that minus a minus okay dt equal to so if you substitute, you have rho ABC x is equal to b a c z because we have that area, the area is equal to AB, and the perimeter is equal to the perimeter is equal to 2B plus 2A. So, of course, A is too small as compared to B. So this is the perimeter. That's from A. That's the perimeter. Which finally should be. Which finally should be rho AC T dx equal to K A squared T dx minus H P T minus T A dx. And of course, we know that for an incompressible medium, CV is equal to CP is equal to C. So we now have rho AC dt dx equal to KA squared T dx minus HP into T TA dx. Here, dx dAK. I think we have the x is there. If the x is there, then because we have the x here, so dividing by the x, we have rho A C dt
this other law, this relevant law that we used to use, this QF is equals to HA. That is changing temperature over there. I thought that thing would have been changing temperature over AC. Now this is not changing QF. Is it the one
of course we have
yes. After that change you use CBBT, Leffer's law, and that other particular relevant law.
Okay.
I thought the formula is T and HA times by change temperature.
Is squared T dx squared
Then changing temperature over there.
minus HP into T minus dA. So, of course, the system does not vary with time. We now have K A squared T over the x squared minus HP T minus dA is equal to 0. So this is the governing equation of a rectangular field.
I like that change in X there.
So let me see if
X.
with this, I think with this, we have 2.256. Okay. dx, and this. We now have 2.257. And because this becomes is equal to this, and the minus BAK is equal to this. That's equal to that, and this equal to that.
Sir,
Huh?
please, why do we have change in x in that change in QSH into the parameter times temperature difference times the change in x? Yes, why do we have that the x there?
The x.
Yes, why is it there? I thought the normal formula is just HA times change in
If you watch,
temperature.
what would it be? If you watch, what would it be? As the x tends to 0 here, you find out that this is a partial derivative.
Okay.
And this remains infinitesimal qx. Of course, you know that it's infinitesimal, insensible, infinitesimal this, infinitesimal that. So as that infinitesimal tends to 0, of course, the partial differential of all, which will become a full derivative if it will become if value will become x. And this is the infinitesimal x. So when you expand this infinitesimal qx, it gives you it gives you this. But this is with the infinitesimal x, and that infinitesimal x is this.
Okay.
Are you getting it?
Okay.
The differential control volume, that is the elemental volume is this.
Okay.
And that elemental volume is the x.
Yes.
And the heat flow in the x will be from the surface,
Alright.
from the lateral surface, from the sides, from the thickness. From the thickness, it becomes from the thickness, it becomes degree x with respect to the x.
Alright.
The lateral surface is with respect to the x. So the dx is not gone. And this dx it also justifies the x here. Because the justification is as a result of this perimeter multiplied by the length, the perimeter of this object, of this thing, multiplied by the length of the thing gives you the area of the thing.
Correct.
I don't know.
Yes, sir.
So that's how it came about with that. So having this 2.257, we now have that this one is 2.258. And that of course having this showed that du, if you have this, it means that du dt is equal to cv dt dt. I don't know whether you're getting this. The du dt is this, which is 2.259. And this is 2.260. So area is equal to cross-sectional area of the thing at any x. at any x. And this one is the perimeter of the fin. Perimeter of the fin, which is equal to 2a to b plus a, which is equal to 2b at any x. At any x, where a is much less than b. So this should be taken as perimeter of the fin. Perimeter of the fin. Okay. So and finally, we now have that rho a c. Of course, I substantiated it here. So I substantiated it here, and we can call it. Okay, yeah, CV. This CV is equal to C. Of course, you can see it's equal to C. So finally, this one becomes. So this one becomes 2.261. 2.261. And this one becomes. This one now becomes 2.262. So 2.262. And I can call this, okay, it's still this way. So having gotten this, what's the difference between this and that? The difference between this and that is that this is equal to 0, which I later erased. Okay, you can leave it that way. Let's make this statement at steady state. At steady state, what happens with t? It is equal to 0. T is thus a function of x. Is that not only a function of x only, so that the square t will be x squared is equal to the square t over x squared. Therefore, Ka the square t over the x squared minus h is equal to t minus t is equal to 2.260. Okay, good. Thank you. So we can also state it this way, or the square t over the x squared is equal to xp over k a into t minus t. So call this 2.26. So this is the governing equation of the rectangular fin. So without wasting time, we get into the solution. You can see yesterday I was telling you we get the governing equation, and this governing equation is known as what? The applicable equation. So this is the applicable equation for a rectangular fin. You can also apply to other fins of constant crossing, such as triangular, symmetrical fins of constant crossing. So this is the standard applicable equation of a fin, such as rectangular or any fin of constant what? Constant what? Crossing. Okay, so now we've got through the applicable equation. The next thing is what? The boundary condition. So let's
I have a question. Okay, so sir, here we are saying that the perimeter, since A is so small, that we'll just consider the perimeter as 2B, right? We're going to take A out. So even in this equation 2.61, when we are calculating the perimeter, we're going to also consider it only as 2B and not 2B plus 2A.
My advice is that it depends on your design. It depends on the design. So I would advise you to make use of the perimeter. What we call the perimeter. What do I mean? Perimeter. And what is the perimeter of this? Of this?
Round, like 2A plus 2B.
So you can now compare it with 2B.
Okay.
But you can now compare it with 2B. You find out that it might almost be the same. One thing with engineering is its practical nature, its experimental nature. You don't just its practical nature, justifies it. You can get 2A plus 2B and compare. If they are near, you can say 2B. They are not. You go on with the perimeter. So let me make a comment. The comment here is equation 2.4 is the governing of or the applicable equation. Applicable equation 4. Applicable equation 4, a rectangle. A rectangular thing of constant cross-sectional area. It is also applicable to the field of any to the field of any shape. The field of any other shape, if the cross-sectional area and the perimeter are constant. Constant over its length.
After that, CV is equals to CP equals to C.
Okay, so having made this comment,
3 by dx.
having made this comment, we have solution.
2.26 divided by
Solution of equation.
but
Equation 2.264.
okay, so something is missing in that equation above 2.61. Above that 2.26 to the x. So that is equal to and then dot infinitesimal x, so that when you divide through by infinitesimal x on all of them, it now comes to 1. Then also above that too, the one below.
Okay. Thank you. Okay, without wasting time, we want to all right. So the solution of this equation is what is given to be what? Let theta be t minus t. Let's theta be t minus t. Let theta be t minus t. And such that square theta over the x squared is equal to hb over ka theta. Remember? Let's So we have this is 2.26. This is 2.266. This is 2.267. Of course, this is what can you infer from this equation? What can you infer from this equation? You know, we converted that to that in order to be able to do what? Huh? We converted this to that in order to do what? To get the solution of this, to get the solution of this equation. Now, what is this equation? Of course, you can see that this equation is a homogeneous linear equation. It's a homogeneous linear second order differential equation. Is that not? And it is unique in its nature. Then, as a mathematician, how do you solve this kind of thing? What?
It's not homogeneous. If it is homogeneous, it will be equated to 0.
If you cross over t is still a function of s. If you cross over t, it's going to be minus, it's still going to be equal to 0 because the variable there is t. The function there actually is t. And t is on both equations. So probably if you cross it over, you're going to have that squared over the x. You get? If you like replace that dt with y
What do you call
y.
it?
It's homogeneous. It's homogeneous from 2.2.
Yes, it's homogeneous.
So okay, let's assume one. This is homogeneous. This is linear.
So it's not linear.
This is and it's a second order differential equation. So having seen this kind of equation, something should occur in your mind. Something should occur in your mind. To find out that this has not been the equation we've been getting all this while. So that means the structure of this equation has a particular theory. It has a theory that the differential equation there is this theory of differential equation that the differential equation of this nature has a solution function. That is a differential equation of this nature has a solution function. It has a solution function, and that the general solution function is given by this equation. That is a second order differential equation. That's this equation is a second order differential equation. So linear homogeneous second order differential equation. And that there is a theory of differential equation that there is this fundamental theory of differential equation that states that this equation has a linearly independent function, solution function. It has a linearly independent solution function. And the general solution, and that the general solution is the linear combination of these solution functions. It says that it has a linearly independent solution function theta, and that the general solution, we are trying to get the general solution to the applicable equation, and that the general solution is a linear combination of this solution function. Is the linear combination of this solution function. So that the